session after coffee and tea break. We have two presentations in this session, and first presentation by Elizabeth Hunke from Los Alamos. And Elizabeth is Rothschild Fellow in our program, so it's a very distinguished person. So, please.
All right, thank you. So this talk is going to be a little bit different. I mostly know about the CICE model that I've built over many years for global climate modeling, and in that model, as of the moment, we don't have any waves. We don't have any wave-ice interactions, and so I'm not going to talk about that. For this workshop, which is ice-fluid interactions, I decided to talk about the ice-fluid interactions within the sea ice itself rather than the interactions with the ocean, although the ocean is certainly involved here. So what I'm going to focus on is the surface water that we carry around on top of the ice, and also the brine that's within the ice, within the brine pockets. That's part of the mushy layer thermodynamics. And I really like this slide that Danny showed first, which shows it's a pretty good description or illustration of the various processes that we have in the CICE sea ice model. And it's pretty complicated. We have a lot of different things in there. But today I'm going to focus on the things that have to do with water on top of the ice, such as the surface melt, some of which runs into the melt ponds or surface water. And then inside the ice we have brine, which can drain out. We have rain that can percolate through. Those are the things that I'm going to look at. So first, just to orient us again, I've explained this a few times now, but for those of you who weren't here earlier, the ice within a single grid cell within the sea ice model is divided up into thickness categories. And the reason for doing that is so that we can better resolve the thermodynamic growth and melt rates in thinner ice as opposed to thicker ice. So what we typically have in the climate model is a ice thickness distribution where we have just 5 categories, a thicker one down through the thinner ones. They each have some amount of snow on them, or maybe no snow at all. And they also can have, they don't have to, but they can have liquid water on top of them. And then for each one of these thickness categories, we calculate the thermodynamic, basically a conduction equation through the depth of the snow in the ice, forcing that with fluxes of things like latent and sensible heats, long wave, short wave, reflected short wave, and heat fluxes at the bottom of the ice. And we do that for each category. So our thickness distribution essentially increases the resolution of our thermodynamics on the grid. Now for the surface water, first I want to say we tend to just call this generically melt ponds in the model, but that's not quite accurate, because we're not just modeling the melt ponds. We're modeling or carrying around, keeping track of all of the surface water that's on top of the ice, whether it's in a pond or not. Okay, and so over the years we've done this in different ways. Originally, we didn't have an explicit parameterization for this surface water. It was implicit in our shortwave parameterization, where we basically had a formula for the albedo, and it was tuned to observational data, but the observational data had melt ponds in it, and so the albedo in our formula reflected that difference in albedo in the summertime. So you could say that somehow that was an implicit parameterization of ponds or surface water in the model. Now, that was a long time ago. Since then, we put in a very complicated multiple scattering radiation scheme. And in order to test that, it actually requires that you have ponds or surface water. You can't run it without them. And so there's a very crude description in there for the radiation scheme, which we don't use for anything except for testing. But then for the last round of IPCC, some of my colleagues at NCAR implemented an explicit pond scheme where they were actually modeling some of the processes that go into ponds. However, those processes were often modeled in terms of empirical functions that were again based on observational data, but the processes themselves were empirical. And then, since then, Daniela Flacco and Danny Feltham and some others put in a physics-based pond scheme, it's also explicit, where it now is based on this ice thickness distribution that's in the model. And so what they do is allow water that's coming from somewhere. It's maybe melted snow, it may be melted ice, it can be rain that falls onto the ice. They let that pool in the thinnest category of the ice, and then it may fill up into the thicker categories if there's really a lot of water. But here they use, again, I think it's an empirical formula for determining what the area coverage of that pond is on that category. And then I took those ideas, which were really cool. They put in a lot of the physics and combined that with some of the assumptions that were made in the old CCSM4 one, and created another scheme, which I call the level ice scheme. And the reason that I call it that is because now we're actually carrying the pond area and volume on the fraction of the ice that's actually level, as opposed to deformed ice. So one of the things that we have available in the model is the area fraction and the volume of deformed ice. We just keep track of that. And so we put the ponds wherever the ice is not deformed, and that can be on any of the categories. So that's the scheme that I'm going to talk about today, but I suspect that it's actually very similar to this one. There is a significant difference, which I'll come to later, but I'll be talking about the level ice pond scheme. For both of those last two, this is the type of physics that we have in there. As I said, the surface water volume is fed by meltwater from ice or snow, by rain, and depending on how you have the model configured, it can also be fed by water percolating up through the ice from below. These water tends to pool on the thinner ice or on level ice, and if there's any snow on the ice, then that water stays hidden. It's down under the ice, or down under the snow. When the ice warms up, it becomes permeable, and that water can drain through to the ocean. And when it becomes cold, it can refreeze at the top, either as a plate of ice over the surface of a pond, for example, or it can get converted into snow ice. If these ponds are refrozen at the top and it snows, then snow collects on top of them, and that again hides that pond, so you don't see this darker color. And then finally, they are transported on the sea ice as the ice moves around. Now the ponds in the Arctic and the Antarctic look a little different, and I don't know if it's just sun angle or if there's really something fundamentally different. But in the Arctic, you do see these beautiful jewel-colored ponds, and in the Antarctic there are ponds, not very many, not nearly as many like you see in the Arctic, but they tend to be slushy, and I think that's because there's a lot more snow in the Antarctic. So the liquid water tends to stay hidden by the snow, and occasionally you see it show up. This is a photograph of an ice floe next to a ship in the Southern Ocean, in the Weddell Sea, where we got out, and this was Steve Ackley and I, actually, we got out and took a couple of ice cores right here. But you can see the tracks show up really well, and this was a very thin ice floe. I think it was, I remember it being 20 centimeters is what we were standing on, which is a little scary. but it was pretty warm and it was slushy under there. So you're seeing very wet ice underneath that snow. Okay, so that's the part about the surface water. Now let's go down inside the ice and talk about the mushy thermodynamics. And I apologize to those of you who saw this before a couple of weeks ago, but there's not very many that are repeated. The thermodynamics that we use in the model now is a fairly new formulation to this model, where it's based on mushy layer theory, and all that means is that the ice is considered a mixture of solid ice and brine. So it's a solid fluid mixture. And what happens is, as the ice starts to grow, these ice crystals form, and there's a lot of fluid in between them. When the ice is forming, the atmosphere tends to be very cold. The ocean is very warm. We have cold over warm. That by itself can set up convection within the ice. But in addition to that, as the sea ice is forming, it's tending to reject the salt that's in it. And so it's forming more up here close to the air-ice interface where it's colder. And so this part of the mush tends to be saltier than this part down here, which is a little bit fresher. So those two things together both induce convection within this mushy layer as it's forming. So what happens is the brine at the top tends to drain out, and meanwhile there's relatively fresher ocean water coming in from below. And that's when the ice is forming. When it gets warmer, then these brine pockets, which are trapped in the ice because it's been so cold, start to connect to each other. And you sort of see that here. It's hard to see, but these three connect. And the brine channels that this forms tend to be vertical just because of gravity. And I should say that this is not just melting and freezing. There's some dissolution because these things are salty, but that's a detail. So what you end up eventually is these kind of vertical channels through the ice, and any liquid water that's up at the top of the ice can drain through them when it becomes porous enough. Now these brine channels are fairly large scale. This one here I think is about the diameter of my thumb, which is pretty big for a ice feature. This is a horizontal, so you can see what they look like from the top. But in global climate models, we can't begin to resolve that. So we parameterize it, and the way we parameterize it is based on these fundamental equations. We conserve energy, we conserve salt. There's a liquidus relation for the ice and the brine, which basically describes what fraction is liquid and what fraction is ice. And then we calculate a vertical velocity through these brine channels based on Darcy flow through a porous medium. And so these are the basic equations that the mushy thermodynamics is based on. There's more, of course, but this is the core of it. Now the geometry that we assume in the model is basically that there's a layer of mush which is sitting next to an open channel. And the open channel is open enough that, you know, whatever flows into it just gets out immediately. And in the mush, we calculate the properties of the mush, like the bulk salinity and that kind of thing, using just a volume averaged equation that combines that property in the brine with that property in the ice. And since this is a math talk, don't blink because this is the only equation you're going to see. Okay, so another assumption that we have in this model is that there's two modes for the brine to drain out. The first one is called the fast mode, and that's this convective process, whereas the ice is freezing, the brine is coming out pretty quickly as it's freezing. And then there's a longer time scale, a slow drainage mode, that's outside of that convecting area. So it's usually convecting down toward the bottom. But if the ice is very thick, then it's not necessarily convecting in there, but it's still draining out very slowly. So up above the mushy layer is the slow drainage mode. And then in addition to that, we have what we refer to as holes in the ice, just macroscopic holes in the ice. And you can think of this as being seal holes, or you can think of it as being places where the melt ponds have actually melted all the way through the ice and make a hole. So these are places where the liquid water on top of the ice can drain out really fast. Okay, so here's an example of some output from the model, averaged over about a decade. And this is running the CICE model in a standalone mode. That's a caveat. Things may actually be different when we run it in coupled mode. But what we see, and the landmass just disappeared. Wow. Anyway, well, this is the Arctic. There's Greenland. What we see is that there's generally too much ice, all seasons, all the time. But this is with the mushy thermodynamics, and this model was tuned using the previous incarnation of the thermodynamics that we had. Boy, this one's not showing up at all. Okay, but anyway, what we see is that if you take the difference of the sea ice thickness between the mushy and the previous thermodynamics parameterization that we had, that in the Arctic it's generally thicker in the mushy case in all seasons. In the Antarctic, you can't see this. This one was actually mostly blue, and then in the winter time, this one was mostly pink with some blue inside of it. Okay, but the other things that I want to talk about here is to explain what changed in the mushy thermodynamics parameterization as compared to that previous thermodynamics parameterization, which is making the ice generally thicker. What's happening there? And so to do that, I want to talk about all the differences between those two approaches. The previous thermodynamics is based on the Bits and Lipscomb thermodynamics model from 1999, but there's a lot of other things that we do in association with that when we run that model, and so that's what most of these differences are. One of the big ones in that model, the Bits and Lipscomb one, is that we assume a profile for the salinity through the depth of the ice, and that profile can change depending on the thickness of the ice. Basically, the magnitude of it changes, but the shape of it does not. And then, of course, in the mushy one, we are actually solving for the salinity. It's a prognostic equation. This liquidus relation, which I said describes the fraction that's brine versus the fraction that is ice, is linear in salinity. The temperature is a linear function of salinity in the previous thermodynamics. And in the mushy layer, it's piecewise linear. It's pretty similar. It's just that for very cold temperatures, we change the slope a little bit. The thermal conductivity here is based on temperature and salinity, again using this fixed profile. In the mushy layer one, it's that volume-weighted combination of the conductivities of the brine and the ice. This one is a little bit complicated, and it's not really a physical thing, but in this older thermodynamics, we had a problem that if there was enough heat converging in the inside of the ice to entirely melt one of the model layers, that model would crash. So that's not a good thing. So what we would do, just to keep it from doing that, is limit the melting to 90% of one of those layers, if that was going to happen, and then redistribute that heat someplace else. And generally, we just put it at the top surface of the ice because that's where it ought to be melting, we think, sometimes. But that's what we would do. And so that was just to kind of get around a numerical problem that we had with that one. In the mushy layer formulation, the brine volume fraction phi can be 1. So we can melt through an entire layer, no problem. This next one is the change in the thickness, and what this is referring to is the method that we use to calculate how much ice melt or froze at the surfaces of the ice. So in this one, the previous one, we would use an enthalpy, which was based on the freezing temperature of the ocean, and assume that that new ice that was freezing would have a salinity of 3.2 parts per thousand. That's just the assumption that we used. And the other thing was that we defined the enthalpy based on a reference temperature of 0 degrees C. So because ice is salty and melts and freezes at some temperature that's less than 0 degrees C, it took a little bit of extra heat to bring the enthalpy up to 0 degrees C. But we just carried that around. We could do it. In the mushy layer formulation, for the bottom, we assume that the porosity is 0.85, and instead of using 0 degrees C, we use the freezing temperature of the ocean as the reference for the enthalpy. And that is extra complicated. It's more bookkeeping, but again, you can do it. It's just bookkeeping. The frazzle is a little bit different. What happens with frazzle in these models is it's really the ocean's responsibility to figure out how much heat content basically you have available as frazzle ice. So the ocean model says, oh, I need to freeze this much ice in order to keep my temperature, in a physical state. And they hand us that potential to form ice. And then it's up to us to decide how much ice we actually freeze and how much of it stays as brine. And so what we do in the model, in the Bits and Lipscomb, or the previous thermodynamics as a whole, I shouldn't attribute this to Bits and Lipscomb, but we would use the salinity based on the salinity profile, and we assumed that the enthalpy of the newly freezing ice was the density times the latent heat of fusion. Pretty simple. In the mushy layer, we have a lot more flexibility, so we choose the salinity to be 3 parts per thousand less than whatever the ocean salinity is, and then we say that the brine salinity is a little bit bigger than that. So that's the assumption that we use. Flushing is this process where the surface water goes down through the ice and flushes out whatever's in there, salt, nutrients, whatever it is. In the older thermodynamics, we didn't allow, we allowed the surface water to leave the ice and go into the ocean, but in doing so, it did not change the temperature or the salinity of the ice. And now it does. And in addition, for this flushing, we also have this macroscopic drainage parameter with a time scale of 10 days. And finally, snow ice formation. When you have this liquid water, like the picture I showed you in the Antarctic, you have this liquid water on the surface of the ice, and when it gets really cold, that can refreeze. And what we used to do was pretty simple. We would say that it refreezes when the surface of the ice, in between the ice and the snow, depresses below sea level. And then what we would do is compact that depth, which is basically based on the snow density, down to a depth based on the ice density that brings that interface back to sea level. So it's based on isostatic balances, but we were compacting the snow. We weren't adding any seawater to it or liquid water to it or anything. In the mushy layer now, we're actually infiltrating that snow with seawater and then freezing that. Okay, so that's a long explanation of the differences. What I want to show you now in these columns is for the northern hemisphere and the southern hemisphere, the relative change in the total ice volume in that hemisphere due to each one of these differences. Okay, so for these are absolute values. There's no sign information here. But I've put the numbers here, and then these bars are basically a sideways histogram plot. So the length of these bars correspond relatively to these numbers. And what we find in the northern hemisphere again in the standalone sea ice model, is that the change from a fixed profile in salinity to the solving for the salinity actually makes the biggest difference in the northern hemisphere thickness. So that's important. What's going on here is it's actually all about the profile values at the top and the bottom of the ice. I think what's in the middle doesn't matter so much, but it's the enthalpy at the top and the enthalpy at the bottom that really matters. And then the second one is this flushing parameterization. Because we have all this liquid meltwater, we have melt ponds on top of the ice, this one actually does pop out as being important. And these other ones, like thermal conductivity, this numerical thing fortunately isn't huge. They don't make so much difference in the Arctic. In the Antarctic, the story is a little bit different. And I've changed the color to green because the scale is different, okay, in my bars. These numbers are pretty small, so in order for you to see them, I enlarged them a little bit. But in the Antarctic, what we see that's important is the enthalpy at the bottom of the ice. It's really important. The second in line is snow ice formation, and third in line, paddle like this, is frazzle. So, and what this reflects are the important processes in the Antarctic. A lot of the changes in the Antarctic are happening at the bottom of the ice. That's true in the Arctic too, but in this case the enthalpy really matters, and frazzle and snow ice are major mechanisms for forming ice. Okay, so those results we're using, let me back up. Those results were using this drainage parameter of 10 days. We did some sensitivities on that to see what would happen. And, oops, I went the wrong way. What we found is that if we use a drainage parameter of 20 days, then the previous incarnation and the mushy ones were reasonably similar. They're a little bit different down here in the summertime. This is in the Arctic. But what is kind of depressing, sobering anyway, is that with this tuning parameter, which is just a kind of a throwaway thing off the cuff, it's not part of our physics parameterization, we can tune it to be whatever we want to with that one. That's actually kind of scary. We can tune away our physics completely. It just overwhelms it. So that to me is a challenge for the modelers or for the observationalists to figure out what is that macroscopic drainage actually in the sea ice, whether it's through melt ponds or seal holes or flowing off the edges of the ice or whatever. That seems to be really important in the standalone model. In the coupled model, who knows, maybe not. Okay, so this is again those same plots that you couldn't see before, but my point here was that there is a seasonal difference in the Antarctic. There's not a seasonal difference in the Arctic, but in the Antarctic it is, where the mushy thermodynamics actually makes the sea ice be thinner than the previous thermodynamics formulation in the summertime and thicker in the winter. Okay, so first a partial summary of where we are. I've talked about, we have these two full physics melt pond parameterizations, and the primary difference between them is where the melt ponds are. In the topo ponds, they pool in the thinnest ice, and in the level ice ones, they pool on the level ice. And then we have to make some assumptions about what area fraction they cover in either of those places. Then we have these two fairly complex thermodynamic parameterizations where the primary difference is how the brine is treated, whether we calculate it explicitly or whether we solve a salinity profile. With that, we can do a lot with the model, just experimenting with things. And so in doing so, we learned some things about the northern and southern hemispheres. First, that in the northern hemisphere, the main differences between these two runs, or two thermodynamics, were between the salinity and the flushing. So that involves the salinity, of course, the enthalpy, particularly at the top and the bottom, but also the permeability within the ice as part of the flushing mechanism. But particularly in the northern hemisphere, this macroscopic pond drainage is really important. And the reason that it's important is because it affects the albedo. How quickly you drain those ponds changes the albedo of the ice pack. If you drain them really quickly, then the ice becomes more white, and you get more reflection. That changes the ice volume. In the southern hemisphere, the main differences are this basal boundary condition, how we treat the enthalpy at the base, and flooding, because of the snow ice formation, is so important in the southern hemisphere. And also that's seasonal. Okay, so for climate modeling, what we've learned over the last few weeks during this program is that we may not actually need this much complexity either for the ponds or for the thermodynamics. Maybe not. It's kind of fun to look at, but we might not need that much complexity. But if you want to look at some details of things like, well, what is important here, then you need it in your model so that you can play with it. Otherwise, you can't. And so one of the things that we at Los Alamos have been really interested in is looking at the sea ice ecosystem. And for this, we do need the complexity because the diatoms, algae, whatever, are actually in the brine pockets. That's what this thing is. And we also see that depending on whether it's the Arctic or the Antarctic, you get different behaviors of the ecosystem. In the Arctic, the algae tends to be at the bottom of the ice, whereas in the Arctic, in this picture, this is the snow layer that has sheared off of a layer of algae at the top, and then there's some algae inside the ice. And that's very different, but that's the reason that they're different is because of the different processes that dominate in the two hemispheres. And we're able to capture all of that in the sea ice model. So the ecosystem, I've called it ecosystem here. In general, it's what I refer to as biogeochemistry, and in some cases it's the chemistry that's the interesting part. So this is an example from the CESM version 1, which is several years old now. It was using the older thermodynamics parameterization with the CESM ponds. This was the empirical one that was explicit. And they did some experiments where they included aerosols in the runs. This is an Earth system model, so the aerosols are in the atmosphere, they fall on the ice, and then once they fall on the ice, they kind of percolate down through the ice, they can get flushed out. And so here are a couple of experiments, climate warming experiments, where in this one, it was a one-time CO2, so the CO2 was at 285 parts per million by volume. And in this experiment, it was twice that. And then I'm showing plots for June and July, summer months, from these two warming experiments. And what we find is that in the warmer climate, there's actually, first let me tell you what you're looking at. This is the enhancement in the shortwave absorption due to aerosols. Okay, so these aerosols are down in the ice, they absorb heat. Okay, and so what you're looking at is the change in the amount of shortwave that's absorbed in the ice due to the aerosols. Okay, so in the one-time CO2, you had a certain amount that's absorbed. In the two-time CO2, there's less, actually, that's absorbed. And the reason is because the climate is warmer here, the ice is more permeable, the aerosols have gotten flushed out of the ice, and so you're not getting as much absorption due to the aerosols because the aerosols aren't there. So, that's kind of an interesting thing about a warming climate that, you might not have thought of immediately. So another example is dimethyl sulfide, or DMS. DMS is a chemical, a molecule, I guess, that's given off by algae, by Phaeocystis, that's in the ocean. And I think it's considered an aerosol. It goes up into the atmosphere, and it's a cloud condensation nucleus. So when the ocean gives this stuff off, it makes more clouds, and that has a feedback on the physical climate system. A colleague of mine, Shanlin Wang, did some experiments. Now these are in 1850, but long runs, where she did a run without DMS in the Earth system model, and then she turned it on just to see what the difference would be, just due to DMS by itself. And what she found is that in the polar regions, they get a lot warmer. That's 5 degrees C, just turning on DMS in the model. So it has a big effect. And because this warms so much, or maybe there's feedback. Do what? Yes.
Turn them off, right? That you get warmer.
Could be. Wait. Let me think.
Because they're scattering.
But no, they're creating more clouds. Yeah. I think this is when she turned them on. I can look. But after the talk, I can look. But anyway, it does get warmer, and associated with that, there's a lot less sea ice, just because of the DMS, whether it's on or off, whichever way it is. So that's what happens when you change the DMS. Now she did another set of runs where, let me look and see what this is. It's the difference between future climate and the pre-industrial run, which is basically 1850. Okay. Okay. So what she finds in this case, when you go into the future, that the amount of DMS itself in the Arctic at least doesn't change very much. It's pretty close to zero. But the fluxes of DMS increase a lot. And the reason that the fluxes increase are because you have less sea ice. So, sea ice is controlling the amount that gets up into the atmosphere. But that's just a binary thing. It's either you have sea ice or you don't have sea ice. This doesn't have anything to do with whether it's flushing or flooding or, salinity or anything. It's just, do you have sea ice or don't you? Okay. So one of the conclusions that I've come to over many years is that what tends to be important about sea ice is where you don't have it. Okay. So this is certainly true with the difference between the albedo of open water and the albedo of ice. That's order 0 in the climate system. And that's the most important thing, where you have open water. It's not where you have ice, it's where you have the open water. But we also see this in things like the DMS, where the ice was acting as some sort of barrier between the atmosphere and the ocean. And it's not just for DMS, for heat, for moisture fluxes, for everything. It acts as a barrier. And so what's important in that case is where you don't have ice. I didn't talk about this, but I've also done some work with redistributing the snow across the ice thickness categories, and we allow some of it to blow off into the leads. And it turns out the most important thing in those experiments is how much blows into the leads. It's not what you do with it on top of the ice. So again, it's where there's not ice is what's controlling the simulation. That's at the large scale. You can come up with smaller scales examples, such as these macroscopic holes in the ice. Again, you don't have ice there. That's where stuff is draining. That's what's important, and so on. So this is sobering, depressing. If you're an ice modeler, it's like, oh, geez, why am I doing this? But it's interesting all the same. And we do need to have some of these model details or complexity in order to ask the new questions of the models. You know, the global climate is not the only science question out there. So that's a lot of the reason why we're doing things. And certainly these larger scale ice fluid interactions do have an impact on the climate. So with that, I'm going to stop and take questions. Pat?
Oh,
Pat.
okay.
Pat.
What do you do with the snow when you put it in a lead? It's a very interesting idea. What do you do with it?
Right now it just disappears.
It disappears?
Yeah.
It's-
Well, it would, if I did this connected to an ocean model, it would add to the
Yep,
the freshwater flux and yeah. But I could see that adding the snow to the lead could become some sort of crystallizing nucleus. Yeah.
Since you had only one equation, maybe you can show it to us.
Oh, the one equation? I can actually show you lots and lots of equations. I have them, just not in this talk.
Only
Where was it?
at the beginning, yeah.
That one.
Okay, I wonder, I mean, what is the physical meaning of X bulk? It shouldn't be plus, you know, Phi brine plus 1 minus phi.
It's we are what this is referring to is a bulk quantity across both the ice and the brine. And so, like for instance, with salt, we have a certain amount of salt that's in the brine. So we have a salt content there, and we have a salt content that's in the ice, which is pretty close to zero. And so, using the volume fraction of the ice and the brine, then we can combine them into a bulk quantity.
Equation is not plus, it's minus.
Oh, yeah, that's a typo. I'm sorry. Yes. Sorry, I missed that.
It's good.
Yeah. Okay, my one math question
Very
is
careful.
wrong.
Very careful. You're fine.
Yeah, that's a typo. I'm sorry.
So 2 comments on the Antarctic melt pond that you showed. Those we found that those are mostly saline, and the one that you showed is
Under a
probably due
ridge.
to the
Yes.
ridge loading,
Yes.
which depressed the
Yep.
surface below sea level, and then it caused flooding on that.
Yep.
I've fallen into many of those, but they are all saline.
Uh-huh.
Actually, they're not melt. The other thing on the Arctic melt ponds, Chris Poloshansky has done a lot of work on this, and what I think it might relate to the period of the time delay, because what happens is as the ice warms up, you start to open up pore space, but then if you're melting from the top, you're putting fresh water into that melt pond,
Mm-hmm. And it refreezes.
and it
In the
freezes
pores.
in there, and
Yeah.
then after some period of time, because of the loading or the melting, or everything, it suddenly, it'll release and make the macroscopic channels that you have. So from Chris's work, you might find some element of the time delay between those 2 processes.
Yeah, okay. That's an interesting idea. Danny?
Yeah.
So it was quite interesting comparing your muscular model compared to the previous model for the southern hemisphere. So salt in the snow ice was a thing, and bottom boundary conditions was a thing that were considered to be important. At the risk of making the Fernback model even more complicated, considering you've already said it's complicated enough, there's kind of like a leading order impact of moving away from the bottom boundary condition just being a Stefan condition, moving to what's called a free equation approach, where you look at conservation of heat, salt, and the liquidus curve at the same time.
Mm-hmm.
That makes quite a big impact. And given that's having importance in the Southern Ocean, maybe that's something that could be included.
It can be included, and we actually did this because your postdoc, who became my postdoc,
Well, that's
did it. When that was Adrian Turner. When he came to Los Alamos, he had been working on that, and so we tried it. We implemented in in the code. And in the simulations that I ran, which again were the CICE model in standalone mode, it really didn't make enough difference to be worth the extra complexity of putting it in there. But we did try it.
And the other thing is the snow ice was important, right?
Yes.
But I'm presuming you're saying, oh, let's have some snow ice of this salinity, and the rest of the salt gets bunked into the ocean. Is that right?
Say that again?
How did you choose the salinity of the snow ice? Presumably you've got snow and you've got infiltrated seawater.
Yeah, well, you use the salt that's in the seawater that goes in. You know what volume of seawater
say it
is
doesn't
required to go into the pore space in the
So all
whole
the
in the
seawater
snow.
freezes in situ, none of the salt escapes. Is that what you said?
The seawater.
None of the salt can escape in that situation.
That's a good question. I don't remember whether any of it escapes.
It goes down.
Yeah.
Okay.
One reason it goes down is that you put the seawater into the top and you've really made the ice a lot warmer. So it's a lot more open all the way down, so when it freezes from the top, you have the...
Oh, I know that's what happens, but I wondered what happens in the model.
Yeah, and I don't remember.
That's why
Yeah, those can be two entirely
jump into
different
the
things.
model.
Yeah, I'll have to look, Danny. I don't remember. Cece.
Regarding that same slide, you described these sensitivities, and I was wondering if they were independent. For example, you described flushing and the salinity difference, and presumably flushing causes a salinity difference, but you pinpointed the albedo as the reason that flushing was important. Is that
they're certainly not entirely independent, and it was pretty hard to actually get these numbers out. You had to take processes out, and in some cases we had to start with the old thermodynamics and add a few in, and then combine. You know, it was pretty complicated. So this is a rough estimate, but
it's just interesting to me how similar the flushing and the salinity are, and yet you identified albedo and the flushing changing the albedo, but not the salinity changing the albedo. Just a point.
Yeah. Well, that's right. I think that's true though. For the flushing case, I think the albedo is the primary thing, but for the salinity, it's the amount of growth at the top and the bottom. But then that is related to the delta thickness one. So they're not independent. Yeah.
Okay, thank you very much, Elizabeth.
Thanks.
The next presentation.